Hello everybody, welcome back to another episode of the problem solving series. I think this is gonna be the last video for a little while, so I don't know, I'm having mixed emotions. This is kind of the end of the mechanics sequence for most physics classes for the one that I'm teaching as well. So yeah, this is gonna be, I'm sure everyone watching this is like, yes, finally we're done. So yeah, without further ado, let's just get into it. So today is going to be kind of similar to the fluids video. I'm going to be covering temperature, heat, and thermodynamics. So a lot of those phrases sound very similar to one another, and all these concepts I think are loosely related to each other, but there's kind of all these little subtopics, and there's a large breadth of things that we cover underneath this umbrella, but we don't go too deep at this level of physics. So first thing I'll talk about is just that temperature. So I guess we'll even go back a little bit further, which we maybe is a little bit more chemistry, but everything around us is matter, and matter is made up of tiny little molecules and atoms. And although we can't see it, even in solids, which they are kind of locked into place, these atoms are, at least in those states, they're vibrating, they're moving, they have a little bit of energy to them. For things like fluids, they are a little bit more, freer to move, and for gases, they are very free to move around us all the time. Turns out the speed of these particles and the kind of it's going to be different for all of them, but there is an overall average speed that particles in a collection of gas, liquid, or solid will have, and that is directly related to the overall temperature of that object. So the temperature and pressure are both generally these macroscopic quantities that we use to describe an entire collection of particles. But each of those particles has their own individual microstates that describes that individual particle. But then we have these broader variables and characteristics that we can use to describe the collective behavior as a whole. So really interesting stuff. How we derive all of that is very complicated, but that at least we can use here and kind of exploit some of the results that a lot of really hard math has discovered for us. So the main thing relating temperature and velocity is that the average speed of, now this is going to be particularly for gas molecules, the average speed for gas molecules we can then write in terms of the temperature, and that's going to be the square root of 3 times the Boltzmann constant, so that's Kb, times the temperature divided by the average mass of one of those I'll stick with particles so it's a little bit more general, but just so you know, it could be atoms, it could be molecules, whatever it is that you're working with. So the Boltzmann constant is 1.38 times 10 to the negative 23 joules per Kelvin. So that temperature in that equation is going to be in Kelvin, which if we do some temperature scaling things, which I'll also just kind of throw that up on the screen, the temperature in Kelvin is equal to the temperature in Celsius plus 273. And then I'll also throw up, although I can't remember it off the top of my head to just say it, the conversion factor from going from Fahrenheit to Celsius. Hopefully your teachers and professors won't be so mean that they would give you temperature in Fahrenheit and then you have to convert it all the way to Kelvin and then plug it into there. But that is one of the ways that we can think about it. There's other relationships that we can then gain from kind of getting this understanding that having more temperature means that those molecules in objects are moving more. So again, for gases, we do get that velocity relationship, but we also have this ideal gas law that tells us about how the pressure can be affected, and depending on the constraints of what container you have or what your system and your environment looks like, also the volume. So again, this is more so of an equation that you get introduced in chemistry, which depending on when you're taking this physics course, you might already be really familiar with. But we have the pressure times the volume is equal to the number of particles that you have times the Boltzmann constant times the temperature, again, temperature in Kelvin. We can also use Avogadro's number to write that in terms of the number of moles, and I think it's the ideal gas constant. I honestly forgot the name of this constant, but it's a capital R. So we can write pressure times volume is equal to the number of moles, which is a lowercase n, times the ideal gas constant, capital R, times the temperature, still in Kelvin. And from this, we can also get another relationship just strictly going from the number of particles to the number of moles, and that's going to be using Avogadro's number as a unit conversion, essentially. Avogadro's number, for anyone who hasn't seen it before or maybe just needs a reminder, we denote this with a capital N with a subscript capital A in this video and in a lot of physics textbooks, and that just is 6.022 times 10 to the 23 parts per mole. So, and again, that I'm going to just keep saying parts and particles, and that's just going to stand for atoms or molecules depending on what your gas is made up of. So that is really handy. The ideal gas law, because it has that pressure in it, I feel like a lot of the times ideal gas law problems can be paired with buoyant force or fluid type problems. So just kind of keep in mind that those things could be linked to one another in a problem that you see, just because we have that pressure as well. The other way that then temperature can affect gases, liquids, and solids is going to be thermal expansion. So when we heat something up, and I feel like this becomes, it's more clear for solids, but when you heat up solids, the bonds that keep atoms in their kind of solid structure can vibrate a little bit, and then those can stretch apart as the atoms themselves get more energy and are trying to fight those bonds a little bit more. So when things heat up, we get thermal expansion, and when things cool down, we get them compressing. So we have an equation for linear expansion, which is that the change in length is equal to the linear thermal expansion coefficient, something like that. It's an alpha. For materials, you would just look up that alpha value in a chart unless it's something that you're specifically solving for. But that change in length is equal to alpha times your original length times the change in temperature. And then we also have a volume thermal expansion, which is the change in volume is equal to beta times your original volume times the change in T. Again, beta, similar to alpha, is just going to be the volume thermal coefficient. And you would look that up in a chart depending on what material is expanding. All of that is to kind of summarize the way that increasing temperature or decreasing temperature has effects on the objects around it in terms of the velocity and then the length or volume or pressure that it is that object is exerting on the world around it. We can also then switch gears, and we'll talk about our next subtopic, which is going to be heat. First thing I guess I want to cover is just the physics definition of what heat is, since we have so many kind of English terms going on in this video that are all kind of could be exchanged with one another when we're, again, just kind of talking colloquially, but within the physics language means something very specific. So heat is the energy transfer that comes between objects because of a temperature difference. So heat is going to be the energy that'll flow from a warmer object to a colder object. So it does always move from warm to cold. And because of this, we can get heat going, or we can represent and describe heat using the specific heat equation. So that would be for a given amount of mass of some substance. If we raise it by a certain temperature or change its temperature by a certain amount, that mass times that substance's heat capacity times whatever the temperature change is equal to the heat that that the substance has then gained. If that change in temperature is positive, if the change in temperature is negative, then that would be the amount of heat lost. And we also can measure or describe heat required to go through a phase change. So a lot of the times, and that's just going to be heat is capital Q. So we have the specific heat equation, which is capital Q, is mc delta T. And then we have the latent heat equation, which is Q equals M times L, where L is the latent heat. And that describes the amount of energy needed or the amount of heat needed to go into a system or go into a substance that, even though we'll use water, for example. So even though, let's say we've raised the temperature of water to get to 100 degrees Celsius, so it's at boiling point, there needs to be additional energy put into the substance to go through the phase change of basically breaking all of those liquid bonds so that way it can become a gas. So there needs to be, before, if you have basically, let's just say we're heating up a cup of water and we ultimately want to get it to vapor that, I don't know, is 105 degrees Celsius. And I don't know, I'm making up stuff off the top of my head. So let's say we start at 70 and we want to eventually heat it up to 105. So we would first break that up as, and we want to know how much heat we need. We would break that up as first the amount of heat that we need to get the water from the 70 degrees Celsius to the 100 degrees Celsius. Then there's amount of heat needed to just do the phase change to get it from liquid to gas. Then there would be additional heat needed to then get the gas molecules warmed up from the 100 degrees to the 105 degrees. So that's kind of really basic and simple. All those equations, so latent heat and then specific heat, typically get used in what are called calorimetry problems, which are basically you have a group of objects that are in contact with each other that could all be at different temperatures. And if you give all of those objects enough time, they will settle all into sharing the same temperature. And the amount of heat that's going to be lost by the hotter objects is going to be gained by the cooler objects until they're all in thermal equilibrium with one another. So depending on the textbook, they kind of set up these types of problems in a weird way. I personally like to set them up in that the heat lost is equal to the heat gained, and then looking and kind of keeping stock of like, okay, what things are losing heat, what things are gaining heat. The processes that are gaining heat, I would all put on the heat gain side, and everything that's losing heat, I would put on the heat lost side. And I do go through a calorimetry problem in the voiceover because I know that they could be kind of complicated. So you'll be able to see a full-blown example there. But the two main equations, or I guess maybe three, I'll include the Q lost equals Q gained, is going to be that relationship that heat lost is equal to heat gained in an isolated system, which is typically the assumption that we can always make. And then that specific heat is going to be Q equals mc delta T, and latent heat is Q equals M times L. The last subtopic that I want to touch on in this umbrella of heat and temperature is thermodynamics. So the first law of thermodynamics, which is the one of the two main equations that I'm going to talk about here, describes how heat going into a system is going to affect its internal energy and also any work that the gas is able to do. So again, this is, well, I guess maybe not again, but this is going to be for gases primarily. And it's just describing the energy relationship for gases, taking into account the heat and the work that the gas can do. So I guess first, generally, we could describe the internal energy of the gas for a monatomic gas, so single atom gas, is going to be 3/2 times the number of particles times Boltzmann constant times the temperature in Kelvin, or if we want to use the number of moles instead, that would be 3/2 little n times ideal gas constant capital R times the temperature. At the very beginning of this, the average velocity of the gas molecules being related to temperature. If we then use that velocity to get the average kinetic energy for the collection of gas, that would be equal to the internal energy, and the internal energy is equal to what I just said. So we have that. Work done by gas is equal to the pressure of the gas times the change in volume. So if a gas has enough pressure or has increased its temperature enough and it's in a container that the volume can change, and that volume increases, then the gas is doing positive work by being able to change that velocity to be an increase, or that velocity, have that volume be an increase in volume. If there's external work pressing and compressing and making that volume decrease, then the work isn't being done by the gas. So you would write the work being done by the gas as being negative, since instead we have work being done onto the gas, which, I mean, our signs for work have always been a little wonky, but this is definitely takes the cake. But keep in mind that the work done by gas would be positive if the volume is increasing and negative if the volume is decreasing. That should help keep your signs straight, and that work is just equal to pressure times change in V. If instead for some reason you were looking for the work done on a gas, then it would just be negative pressure times change in V to give you that. And then the first law of thermodynamics, which is going to relate that work, the change in internal energy and heat, is that the change in internal energy is equal to the heat added into the system minus the work done by the system. So another way that you could think about this, which would just be adding that work to the other side, is that the amount of heat external going into a system can go into allowing the gas to do work on its container, or increase the overall temperature to raise the internal energy of the gas itself. And then the last thing I want to talk about with thermodynamics is going to be entropy. So entropy is a description of the amount of order or disorder that you have in a system. For an isolated system, which is the only type that we would be considering at this level of physics, your change in entropy is going to be equal to the change in heat divided by the temperature that the heat is being added at. And that should always be positive. So that change in entropy should always be positive or equal to 0. So equal to or greater than 0. And that is because an isolated system allowed to evolve in that way with heat added can only get more and more disordered as time goes on. If it were to get more ordered, you would need something else to be able to do that. So things want to get into equilibrium, they want to spread out, gases want to be away from each other, and the more that they are able to do that, the more disorder that we have, and therefore the more entropy that we have. So yeah, I think that's everything that I have for the intro. I know it was kind of long. We will go into the voiceover portion where I will show you some examples. Since this is such a kind of mixed bag of a bunch of different topics, I chose problems where I'm able to mix and match a lot of the equations that we talked about here. You can see these very separated, and I don't think that you would typically... I picked things that you would typically see or you could reasonably expect to be paired together, but that's definitely not the only way that you can see these concepts, and there definitely are a ton of standalone problems. I just didn't want to have to do, a bunch of examples in this video and be able to hit kind of a bunch of concepts within only a couple problems. So let's get into those so you can see how to use these darn things.
The average speed of an air molecule is 500 meters per second. What is the temperature of the air? If there are 5 moles of air in a container with volume 1 meter cubed, what is the pressure of the gas? So we're going to do a little combination of kinetic theory and gases and ideal gas law. So we first have our RMS speed, or our average speed, is that 500 meters per second, and we want to know the temperature. So we have an equation that directly relates these two that comes from conservation of energy. So V RMS is equal to 3 kT over m all over a square root. So if we want to rearrange this to get t by itself, we could square both sides. So we'll get V RMS squared is 3 kT over m. And then we could multiply by the reciprocal. So m over 3k to get the temperature by itself. And then we can substitute from here. Oh, I don't know the mass of an average air molecule. Okay, I forgot to put down this, so we're going to say that the mass is 5 times 10 to the minus 26 kilograms. But once we have that, then we can put in 5 times 10 to the minus 26 times 500 squared over 3 times 1.38 times 10 to the minus 23. And that is going to give us a temperature of 302 Kelvin. So then, if we are given that our number of moles is 5 and our volume is 1 meter cubed, then we can use PV equals nRT to get the pressure. So we'll divide volume to get pressure by itself, and we'll have 5 times 8.31 times 302 over 1. And that gives me a pressure of 12,548 newtons per meter squared. Okay, keeping with our theme of really mixing and matching a lot of these or a lot of these problems, I guess I should say, for heat, temperature, and thermodynamics, we are going to combine a calorimetry problem with a linear expansion, or I guess a volume expansion, and an entropy question. So let's get to it. So we have an aluminum cup. I didn't write these down, but I will write them here. The specific heat for aluminum, which I'll write as Ca, is going to be 900 joules per kilogram per Kelvin. And that's going to be filled with water at 37 degrees. The specific heat of water is 4186. And we want to know the amount of heat is required to bring the cup with water to 100 degrees Celsius and then boiling. So Q So we will first have, or I guess we'll have a couple heats here. So our Q total is going to be the heat to raise the aluminum cup to 100 degrees, plus the heat to bring the water to 100 degrees. Then we'll have the amount of heat needed for the phase change. So water, and I'm just writing kind of little notes to myself of what each of those heats stand for. Then we can plug in the appropriate expression for Q. So for aluminum, that will be the mass of our aluminum cup times the specific heat times its change in temperature. So for the aluminum, that will be 100 minus 20. My trick for these is usually to write out the delta t's first before just plugging them in. I guess maybe I also want to plug in the Q is mc delta t equation for specific heat and raising the temperature of a substance, and then we have the latent heat equation for phase changes, where that just is mass times L. So that's for aluminum. For water, we're going to have the mass of water times the specific heat of water times its change in temperature, which is going to be 100 minus 37. And then let me scoot this over a little bit so I can fit the last thing on this line, which is going to be plus the mass of water times the latent heat of vapor. So I'll just write that as L, and then I'll kind of pop over here. That L is going to be 2,260, and that's kilojoules per kilogram, so I'm just going to write that as 10 to the 3 joules per kilogram. Hey, I forgot to put in masses, so I'm just going to make up that they're both half a kilogram. So we'll say the aluminum is half a kilogram, and the water is half a kilogram, so a thick cup. And then we can substitute everything in and get our total. So Q total is 0.5 times 900 times 80 plus 0.5, 4,186 times 63 plus 0.5 times 2260 times 10 to the third. And all together, that's going to give me a heat of 1.3 times 10 to the sixth joules. Now for our next question, how much has the volume of water expanded just before it starts to boil? We're just going to look at the percentage of the total volume that it's increased. So percent volume increased, and that is just going to be, so basically all that's saying is that's going to be the change in volume over the original volume times 100%. If we look at our equation for volume expansion, that is delta V equals beta V0 times delta T. So we could divide out our V0 and multiply both sides by 100% to get what the answer in the format that they're looking for. But I'm just going to leave it as delta V over V0 for the moment. So delta V over V0 is going to be beta times delta T. Our beta for water is 210 times 10 to the minus 6. And our delta T we know from the previous part is 100 minus 36, which is 63. So we could plug both of those numbers in. That gives delta V over V0 equals 0.013. And now we'll go ahead, I'll throw in that times 100% on both sides. So we'll get our percent increase to be 1.3%. And lastly, we want to know the change in entropy that occurred by this amount of heat being put into this system. So we have the change in entropy is equal to Q divided by T, where our Q will be 1.3 times 10 to the 6th, and the temperature is going to be, oh sorry, we're just looking for the Q from our phase change. So we didn't explicitly calculate that, but we do have it written. I'll zoom out a little bit so it's on the same page. We do have it written just right here. So I'm going to plug that in, 0.5 times 22680 times 10 to the 3. And then the temperature that the phase change happens is going to be at 100 degrees Celsius, which would be 373 degrees Kelvin. So we want to make sure that T is put back into Kelvin for entropy. And our entropy change is going to be 3029. And I guess that will be joules per Kelvin. You throw those units on there. Okay, and lastly, now we're going to go ahead and combine ideal gas with some thermodynamics. So we have an ideal gas being held at atmospheric pressure, so our P is 1 atm, or 10 to the 5 Newton per meter squared, and then I'm just going to put in parentheses, this is held constant. And our initial volume is going to be 0.1 meter cubed. Our initial temperature is 300 Kelvin. Now heat is going to be added into the system, and our V, I guess maybe I'll call these T1 and V1 instead, where our V2 is going to be 2 times V1, which will end up being 0.2 meters cubed. And we want to know the change in temperature of the gas. So we want to know delta T, which would also be T2 minus T1. We have T1, and we can get the change in temperature using the ideal gas law. So we can also assume that the number of particles or the number of moles that we have aren't changing, which means that we can say P1 V1 over T1 is equal to P2 V2 over T2. We know that P1 and P2 are actually equal to each other because P is held constant. So I'm going to cancel those out. And to simplify our math a little bit, I'm going to go ahead and rewrite that V2 as 2 times V1. So that way we can also go ahead and cancel those volumes. And then we're just going to go ahead and cross multiply. So T1 and T2 will end up with T2 is equal to 2 times T1. So our T2 is going to be equal to 600 Kelvin if we plug in that 300, and our change in T then is 600 minus 300, which would be 300. Okay, so then if we know that, how much heat was added to the system? So the other thing that we can gather before looking at how much heat was added to the system, we're going to go ahead and look at the total, or I guess the thermodynamic equation, which is going to be our change in U is equal to Q minus work done on the gas. So we're solving for Q. We can get delta U using delta T, and then the pressure, volume, and temperature we can also use to get the number of moles that we have in our gas. So let me write out where we're going to go with this. So delta U is going to be 3/2 and our delta T. We have our delta T, but we don't have N, but we could get that from well, we have our pressure, volume, and temperature at both times, so we could really use either of them, but I'll just use the ones. So P1, V1, I'll move this actually a little bit further down, equals nRT1. So P1 V1 over R times T1 is going to be our number of moles. So 10 to the 5, 0.1, 8.31 times 300. And that's going to be 4.01. Almost got a round number. So then we can go ahead and plug that in to delta U. And that's going to be, I'm just going to round that to 2 sig figs, but that'll be 15,000 joules. So I'll go ahead and box that since we're going to need that to plug in to our equation over here. The other thing that we can do is that we can solve for the work done on the gas because we know the pressure is being held constant and we know the change in volume. So I will do that piece over here. So work on gas is negative of the pressure times the change in volume. Since the volume is expanding, this is the other way that we can think about this. Since the volume is expanding, that means that the gas is doing work, and therefore the work done on the gas should be negative, and then the work done by the gas would be positive. So our work on gas, I guess then we wouldn't include that extra negative sign, is going to be our 10 to the 5 times our change in volume is 0.2 minus 0.1. So that'll give us 10 to the 4 joules. And then finally plugging everything into our thermodynamic equation, we'll have 15,000 equals Q minus 10,000, or yeah, that is 10,000, not 10 to the 4. We'll add our 10,000 to the other side, and we would get 25,000 joules is the amount of heat added to the gas.
All right, and there you have it. So that is all that I have for heat, temperature, and thermodynamics. And I guess that's also all I have for mechanics at the moment. So hopefully I will have electricity and magnetism intro videos coming over the summer or possibly in fall of 2021. So if you are going to be a student in that class after you finish up mechanics, please be on the lookout for that. And until next time, happy physicsing. Bye, guys.
What you doing? Are you hiding? Come here. Can you come this way? Can you harm me, girl? Yeah! Good boy.